first colloquium of this year. For this time, we have Manus Visser. He's currently in Cambridge, although he will join us with the Dutch philosophy club. He's an expert in black holes, thermodynamics, quantum gravity, and he will talk about black hole thermodynamics. As usual, we will have 45 minutes of talk, some brief pause, and then we will have 45 minutes for discussion, questions for the public, this public and also the online public. Fergus?
Yeah. Thank you very much for the invitation. Yes, so I'll talk about the holographic dual of black hole thermodynamics. This is based on ongoing research for the past 30 years by many people and also partly by myself, but I'm planning to write a kind of philosophy article about this. Okay, so the biggest clue for quantum gravity, in my opinion, comes from the thermodynamics of black holes, since it suggests some kind of statistical underpinning. And black hole entropy can be viewed as a low energy constraint that every quantum gravity theory has to satisfy. So every quantum gravity theory has to reproduce black hole entropy. As an historical aside, I think this is kind of similar to the UV catastrophe in black body radiation that led Planck to postulate in the sense that that was also kind of a clue that led to quantum mechanics.
But this is really different.
Well, that was based on experimental access, and this is about theory, but our hope is that it will lead to, it's like it gives us some access to quantum gravity. However, so this is a nice story, but however, black hole thermodynamics poses some puzzles. Since it contains certain features that are seemingly different from those in standard textbook thermodynamics. For instance, black hole entropy is famously non-extensive because it scales with the horizon area and not with the volume of a black hole, whatever that may be, because it's very difficult to define the volume even for black holes. And so these and other disanalogies between black hole thermodynamics and standard textbook thermodynamics have led philosophers such as Doherty and Callender to argue that black holes are not really thermodynamics. And so I want to argue today that holography resolves these puzzles surrounding black hole thermodynamics. That is my main thesis. And so in a holographic framework, black holes in the bulk geometry, I will use that terminology very often, are dual to thermal states in the boundary field theory. So a field theory living on the boundary of the bulk. Usually, these thermal states of living on the boundary in the boundary field theory satisfy the standard laws of thermodynamics, as I will show. And so I will develop in this talk, I will develop a holographic dictionary that relates the non-standard laws of black hole thermodynamics to the standard laws of thermodynamics in the field theory. And along the way, I will distinguish two forms of holography or the holographic principle, namely a weak form, which is related to entropy bounds, and a strong form, which is related to the holographic duality. All right, so that is kind of a summary already of my talk, and now I will dive in to the talk. So the plan of the talk is that I will first explain why black hole thermodynamics is puzzling. There are many puzzles related to black hole thermodynamics. A famous one is the black hole information paradox, which I will largely disregard in this talk. I will just focus on a few puzzles that I find interesting and that many people have not really emphasized in the literature, and that I think that holography resolves these problems. Then I will talk about some history and philosophy of holography. Those are maybe big words, but I'll mainly distinguish this weak and strong form of holography. And then I'll explain how holography resolves the puzzles about black hole thermodynamics. Okay, so in the 70s, Bekenstein and Hawking and others have argued that black holes are genuine thermodynamic objects with an energy which is proportional to their mass, a temperature which is it's called the Hawking temperature, is proportional to the so-called surface gravity kappa of the black hole. Notice that it's a quantum effect, so it's proportional to the Planck constant, and it's a relativistic effect and a thermal effect, obviously. And then they also have an entropy called the Bekenstein-Hawking entropy, and this entropy is proportional to the area of the event horizon of a black hole. That's what I denote by A. What's very interesting is that black hole thermodynamics combines GR because it's about gravity and about relativity. It combines GR, Q of T quantum field theory because it's a quantum effect, and thermodynamics into one kind of unity. And what's very interesting about this formula for black hole entropy is that it contains all the constants of nature. So it contains Boltzmann's constant, so it's related to thermodynamics. It contains speed of light, so it's related to relativity. It contains Newton's constant, so it's related to gravity, and it contains Planck's constant. And notice that these three quantities satisfy this first law. All right. Yeah, and then, okay. So now let me describe the first puzzle. So as I said, black hole entropy, or black holes carry an entropy given by the horizon area in Planckian units. So in the second formula, I wrote all the constants of nature, I combined them into Planck's, to the Planck length. So black hole entropy is basically the horizon area divided by Planck squared, Planck length squared in for space-time dimensions. So as I said, black hole entropy scales with the area, not with the volume of a black hole. And this means that black hole entropy is not extensive. So usually in thermodynamics, entropy is extensive. Black hole entropy is not. And the question is why? Why does black hole entropy scale with the area, not with the volume? And obviously this gives a hint for quantum gravity, because you see that this is a quantum gravity effect. It's only finite when G is finite and H bar is finite. So in particular, when you take the classical limit, take H bar to 0, blows up. We take C to infinity, it diverges, and we take G to 0, it also diverges. So it's only finite in quantum gravity. So this gives a hint about what entropy is in quantum gravity, or what the fundamental degrees of freedom are in quantum gravity. And there should be some huge reduction of degrees of freedom, because in quantum field theory, it's a local theory, so there's a degree of freedom associated to every point of space-time. But in that case, entropy scales with volume and not with area. So it must be some kind of there must be some kind of non-local degrees of freedom at play here in quantum gravity. Okay. So I will just now summarize these puzzles, and then later I'll try to resolve them. Right, so Bardeen, Carter, and Hawking have derived the so-called 4 laws of black hole mechanics. So the 0th law is that this surface gravity, so recall that the Hawking temperature is proportional to this surface gravity kappa. And so you can prove basically that kappa is constant over a stationary black hole horizon. For this, you need, well, there are several proofs. For one proof, you need Einstein's field equations. Then there is a so-called first law, relating the variations of the black hole parameters. So relates the mass to the variation, to the horizon area variation, to the angular momentum variation. There's a second law. Classically, it states that the horizon area always or doesn't decrease. That's also just a theorem in differential geometry. Right, and then there's also a third law, which is less important. But what I want to focus on are the work terms. And so they seem to be absent in the first law of black hole mechanics. You could interpret this term as a chemical potential. So if the angular momentum is quantized, then you can interpret it as a charge, and then this omega, which is called the angular velocity, is the associated chemical potential to this charge. But there's no PDV term, and there is no mu dn term, where n is like the number of degrees of freedom or number of atoms, basically. So these work terms, especially PDV and mu dm, seem to be absent. Right, and of course this TdS is associated with this term because T is proportional to kappa and S is proportional to A. Okay, the third puzzle is about the SMAR formula. So stationary black holes in GR can be characterized by three parameters: the mass, the angular momentum, and the electric charge. This is the so-called no-hair theorem. And these black hole parameters are related by the SMAR formula. So SMAR derived this from the first law. And right, so there's just one equation relating all these black hole parameters. What's interesting is that there are dimension-dependent factors in this formula. And you might say, so what? But in standard thermodynamics, there's also a formula relating the thermodynamic parameters for equilibrium states, and that's called the Euler equation, which is E is Ts plus mu n minus PV, which follows basically from extensivity. And so there are no d-dimension dependent factors in this formula, although there are d-dimension dependent factors in this formula. And the question is, how come? And are these two equations related, or can the SMAR formula be written without these factors? So this is more like a technical puzzle. And related to that, this was so previously in the previous slide, I presented the SMAR formula for asymptotically flat black holes. But in asymptotically anti-de Sitter space or de Sitter space, the cosmological constant also appears in the SMAR formula. And then you get the so-called generalized SMAR formula. So you get this extra term. So lambda here is the cosmological constant, and theta is the conjugate quantity, basically. So it's defined as the partial derivative of the mass with respect to the cosmological constant with these parameters kept fixed. And for the question is, what is the thermodynamic interpretation of this extra term? People have speculated about that, and they interpreted the lambda as a pressure, because you can view lambda as a perfect fluid. So you can view the cosmological constant term in the Einstein equation as a perfect fluid. And then the pressure of that fluid is proportional to lambda. And so they interpret lambda as pressure, bulk pressure, and then theta should be the volume. However, I'm actually doubting that interpretation, and I want to present a different interpretation of this particular term. Okay. So I want to focus on these three puzzles, but there are many other conceptual puzzles. As I said, the black hole information loss paradox is black hole evaporation, a unitary process, Then what kind of entropy is black hole entropy? Is it Boltzmann entropy, von Neumann entropy, or a different kind of entropy? What is the statistical origin of black hole thermodynamics? What are the microstates, atoms that make up a black hole? And where do these microstates live? Do they live inside the black hole, outside, or on the horizon? And my claim would be that holography partially or fully resolves these puzzles. All right. Are there any questions so far? Okay, so now on to holography. Yeah, and there is a book by Leonard Susskind, who's one of the kind of inventors of holography. And yeah, we could read this because it's about his visit to Gerard het Hoofd in Utrecht. And since we're in Utrecht, this might be a nice anecdote. So this wildly bizarre behavior reminds me of my joke to Thorlacius that the world inside a black hole might be like a hologram, with the real information being far away on the two-dimensional horizon. String theory goes even further. It places every bit of information, whether in black holes or black newsprint, at the outer edges of the universe, or at infinity if the universe has no end. Every time I started to discuss this idea with het Hoofd, we got stuck at the beginning, but shortly before I left Utrecht for home, Gerard said something that startled. He said that if we could look at the microscopic Planck-sized details on the walls of his office, in principle, they would contain every bit of information about the interior of the room. I don't recall him using the word hologram, but he was clearly thinking the same thing as I was. In some way that we don't understand, every bit of information in the world is stored far away at the most distant boundaries of space. In fact, he had the jump on me. He mentioned a paper a few months old in which he had speculated about this idea. Conversation ended on that note, and we didn't talk much about black holes during my last 2 days in Holland. But when we went back to my hotel that evening, I worked out a detailed argument and proved the point. The maximum amount of information that can possibly be contained in any region of space cannot be greater than what can be stored on the boundary of the region, using no more than 1/4 of a bit per Planck area. Somehow at Hoofd's paper, which preceded my own by several months, went largely unnoticed. Partly that was due to its title, Dimensional Reduction in Quantum Gravity. The term dimensional reduction happens to be a technical physics term that has an entirely different meaning than what het Hoofd intended. I made sure that my paper would not suffer the same fate. So I titled it The World as a Hologram. On the way home, I started to write it all down. I was very excited about the holographic principle, but I also knew that it was going to be very hard to convince anyone else. The world as a hologram, I almost hear the skeptical reaction. He used to be a good physicist, but he's gone completely bonkers. All right, so this is from a popular book by Susskind, but it kind of describes the history of some of the history in his words, I guess. Right, so maybe I should actually first say this. So Hoofd's article appeared in 93 and Suskind's article in 94, and those are kind of the typical first papers on holography. And Susskind coined the term holographic principle, and he also had the word hologram in his title. But even though he didn't remember it, actually het Hoofd mentioned the word hologram in his paper. So he mentioned the analogy between his idea of dimensional reduction. So he kind of coined it as dimensional reduction, but he did use the analogy with hologram, but then kind of Susskind branded it. And so in their paper, they argued for two things, in my opinion. So first is an entropy bound. So the idea is that if you have this room and you try to put matter in it and even more and more and more, at some point it collapses into a black hole. And then if you try to put more and more matter into it, the black hole increases in size. Because if the mass increases, the horizon area also increases. So a fat black hole is larger. And at some point, the horizon area coincides with the boundary of this room, of this office. And that's kind of the entropy bound. So a black hole has the maximum entropy, and this means that the maximum entropy that this room can have is given by the Bekenstein-Hawking entropy. So the entropy bound says that the maximum entropy in a given region of space is given by the area of that region of space measured in Planck units. But they went even further. And this is the opening sentence of Suskind's paper, or the abstract of Suskind's paper. According to it, the combination of quantum mechanics and gravity requires the three-dimensional world to be an image of data that can be stored on a two-dimensional projection, much like a holographic image. So here it means three space-time spatial dimensions. And so that can be, the data can be stored on a two-dimensional projection. So this is kind of the naive picture. So in quantum gravity, the fundamental degrees of freedom live on the boundary. And so this is a picture of a black hole event horizon. And so there should be 1 degree of freedom per Planck squared area. And since you have the entropy is proportional to the area, that means you have basically a full area worth of entropy. The degrees of freedom are really projected on the boundary somehow. But this picture is a bit too naive because as we'll see in examples of holographic duality, the degrees of freedom can live on the boundary of the space-time, not on the horizon. All right, I wanted to mention a different motivation for holography that people sometimes mention, but it's not very well known. And that comes from the gravitational Hamiltonian. So you can prove that the Hamiltonian of any diffeomorphism invariant theory is a boundary term if you evaluate it on shell. So it can be shown very generally that the gravitational Hamiltonian takes this form, where n, so this is a volume integral, so this sigma is some Cauchy slice, n and ni are called the lapse and the shift, and c and ci are the constraint equations. So this is the Hamilton constraint, and this is the momentum constraint. Now, on shell, the constraints vanish. So the volume integral is completely zero. So that's why people often say that the Hamiltonian is zero in GR. But actually, it's a boundary term. So it's an integral over the boundary of this Cauchy slice. So if you take a Cauchy slice of Minkowski space, then it's an integral over spatial infinity.
Is this term with h supposed to be under the integral sign or not?
No. So it's a separate integral itself. So it's it's an integral over d sigma, and then in GR takes a certain form. And it's like nk 1/8 by g. And so this is a generalization of Gauss's law in Newtonian gravity to GR. Because there the mass can also be written as a boundary integral. And so this kind of smells like holography because so due to diffeomorphism invariance, the Hamiltonian is boundary term, and hence like maybe the theory of the underlying theory lives on the boundary. All right, so Now, so based on what I said here, I want to distinguish between two forms of the holographic principle. So I've only stated it in kind of vague terms, but I'll now try to make it a bit more precise. So I will coin the weak holographic principle as the one that states that any complete theory of quantum gravity should exhibit an upper limit to the total number of degrees of freedom in a spatial region with a boundary P. So the total number of degrees of freedom in a region with boundary B is smaller than or equal to the exponent of the Berenstein-Hawking entropy associated with that boundary. So in other words, the entropy of some spatial region is always smaller than the area of that the boundary of that region measured in Planck units. So that's the entropy bound. Now I formulated it here in a kind of non-covariant way because I used the spatial region, but there is a covariant version which was formulated by Raphael Busso. There's very nice review on the holographic principle by him. The strong holographic principle, on the other hand, or gauge gravity duality, is the idea that quantum gravity in the bulk spacetime is dual to a quantum theory living on the boundary of that spacetime. And in this quantum theory, there is no gravity, obviously. So GR in rough terms, GR in the bulk is dual to quantum mechanics on the boundary. And note that these two forms of the holographic principle are very different. This one is much stronger, since it states that a complete theory is equivalent to another theory, whereas it's just a bound on the entropy in a certain region of space.
Why is it obvious that there on the boundary there's not also a gravitational theory?
But that is the gauge gravity duality. I mean, so gravity in the bulk is dual to a quantum theory without gravity on the boundary. That is the statement, basically. Yeah. Okay, so an example of the strong form of the holographic principle is the famous ADS-CFT duality. But this is the best understood example, the most well-studied example. And it states roughly that weakly coupled gravity in a bulk asymptotically anti-de Sitter spacetime, so with negative cosmological constant or negative curvature, is dual to a conformally invariant gauge theory at large N, where N is the rank of the gauge group, and strong at hoofdcoupling living on the conformal boundary of ADS. This is a picture of anti-de Sitter space. So time goes upwards, and spatial slices are hyperbolic spaces, and the conformal boundary is roughly this. So it's like a soup can, and the conformal boundary is the boundary of that can. And what's important for us is that ADS black holes, so there could be a black hole sitting here, those are dual to thermal states living on the boundary of ADS in the conformal field theory. And when I say boundary here, I actually really mean conformal boundary. So it doesn't really live at a particular place. It's kind of, you can rescale the size of this boundary. So the theory is really conformally invariant. That's really important. Okay. Going back to the two forms of the holographic principle, how are they related? And so how should we really understand the holographic principle? And what I want to emphasize is that the entropy bound does not imply a holographic duality. As I said, holographic duality is much stronger. But holographic duality does imply the entropy bound to some extent. Why does entropy bound not imply holographic duality? That's because there might be other explanations of the entropy bound which do not involve the duality. For instance, people try to explain the entropy of some spatial region through vacuum entanglement entropy of quantum fields, Colloquium and Planck length. And there even exist proofs of the covariant entropy bound in semi-classical gravity by Busso, Cassini, Fischer, and Polsena, which do not require a duality. So there are proofs of this bound which do not rely on a duality. However, going the other way, there are derivations of the entropy bound from assuming ADS-CFT. So there is a kind of quantitative check in ADS-CFT that the dual CFT contains an areas worth 12 degrees of freedom.
But that's not a bound, right? That's just when it is that value. Why is the maximum?
Right. That's so the actual covariant entropy bound. I don't think that there is a proof using ADS-CFT, but but that might just be difficult. My expectation is that it might be possible to get read the bound rather than the value. So another aspect of ADS-CFT is the relation between the cosmological constant and the number of colors in the gauge theory. So the gauge theory has like SUN gauge group, for instance, and then N is really that's this N, the number of colors. Or more precisely, there's a relation between the cosmological constant and the central charge, which is the number of field degrees of freedom in the sea. So there's a universal dictionary for this central charge in CFT's dual to Einstein gravity. And that's the following: C is proportional to L to the D minus 2 over Newton's constant, where D is the number of bulk spacetime dimensions, and L is the so-called O curvature radius or ADS radius. And so lambda, the cosmological constant, is related to the curvature radius as 1 over L squared. So there is a relation between C and lambda and G.
I need get Newton's constant in another number of dimensions.
So you can formulate Newton's law of gravity in any number of dimensions, and also Einstein's equation in any number of dimensions. But it scales with, so C is dimensionless. So Newton's constant has dimensions of L to the D minus 2. So for instance, Newton's law, so G has dimensions of length squared in natural units, but there is a generalization of this to any number of dimensions, where this becomes R to the D minus 2 basically, and there might be some prefactors.
Okay, I'll just have to think about whether it's G and everyone separately. Okay.
Okay, and in the canonical example of ADS-CFT, between type 2B string theory on ADS5 plus S5 being dual to N equals 4 super Yang-Mills theory, in 4 dimensions, we have that C is proportional to N squared, where N is the rank of this gauge group. And then the duality or the dictionary between these two theories states that N squared is proportional to this number or to this. But this is the blank, sorry, this is the bulk ADS radius in 5 dimensions, and this is Newton's constant in 5 dimensions. So this is a bit technical, but I'm going to use this later on. Okay, are there any questions about this? Okay, let me then explain how holography resolves the puzzles that I mentioned earlier. Okay, so the first puzzle was about black hole entropy, why it scales with the area rather than the volume. Now in ADS-CFT, as I said, stationary black holes are dual to thermal equilibrium states. And this means that black hole entropy has to be dual to the entropy of these states. Now, black hole entropy scales with the horizon area, so RH to the T minus 2 over G. And as we just saw, so we can divide by L to the D minus 2 and multiply by L to the D minus 2, so we can actually write it in this way, using this dictionary for the central charge. And then you have this extra factor X, which is D minus 2, where X is the ratio between the horizon radius and the bulk egress radius. And the fact that S scales with C, or N squared, is a generic property of a large N gauge theory in the deconfined phase. So you take the gauge theory as UN, you take N to be very large, not as U2, as U3, but very large, up to infinity, let's say. And then you look at not at the confined phase, but at the deconfined phase, where quarks and gluons are really all free. And in that case, you can show that the entropy of that phase scales with N squared. So C, as I said, is proportional to N squared. So this is really the origin, this large N behavior of the entropy in the deconfined phase is really the origin of the area law of black hole entropy. Now, this is not yet extensive, actually, for, let's say, for a CFT living on a sphere at finite temperature. This entropy is not extensive, so it's non-extensive. However, in the large volume limit or large temperature limit, this entropy becomes extensive. So if you take the size of your sphere to be very large, or the temperature to be very large, then the entropy becomes extensive. So then it becomes proportional to the volume. We'll show this in a bit more detail. So if you take L, that's the boundary curvature radius, like the radius of your sphere where the CFT lives, boundary sphere. T is the temperature. Now this combination is scale invariant, it's conformally invariant. So that's why I take the product. So if LT is very large, then you can show that LT becomes proportional to this ratio, X. And so in that case, I can write this in this way. And now the volume is proportional to L to the D minus 2. Because D is the number of bulk spacetime dimensions. So D minus 2 is the number of spatial dimensions on the boundary. Fast. So I have a bulk in D spacetime dimensions. I have a boundary in small d, so d is d plus 1. And if I now take some slice here, then this, let's say this is a sphere. So my ADS is like a R across some, sorry, my CFT lives on R cross S to the S to the D minus, sorry, S to the D minus 1, which is R cross S to the D minus 2. So this is time. Then I have D minus 1 spatial dimensions, but that's the same as big D minus 2. So that's why I have a D minus 2 there. So if I take the radius of my sphere to the power D minus 2, that's proportional to the spatial volume of the sphere. Okay. So in this particular regime, the entropy becomes extensive. Any questions about this? All right. So next, I wanted to talk about puzzles 2 and 3. So puzzle 2 was about why there are no work terms in the first law for black holes, and puzzle 3 was about the SMAR equation. And as I've shown a few years ago, this SMAR equation, which is this equation, where I added this term, because I'm looking at APS black holes, it can be shown that that equation is dual to this equation, which I coined the large N ordinary equation, because it's an ordinary equation for large N gauge theories. And what's interesting about this equation is that there is no PV term. But usually in this ordinary equation, you have a minus PV as well. But that equation follows from extensivity. And since we don't have an extensive system, we don't have that equation. But this equation actually follows from the large N behavior of the thermodynamic quantities. It follows, we'll explain this, maybe I should wait. And then that was about the SMAR equation. And then I also showed that the bulk first law, where I also added this extra term. So I varied cosmological constant, that's called the extended bulk first law, is dual to this boundary first law. And this boundary first law is a standard first law of thermodynamics, where you do have a PdV term and you do have a mu dn term. So you do have work terms in the CFT, but not in bulk. Okay, so where does this, now I want to focus more on this one and then I'll explain this one. So where does this large N ordinary equation come from? So it comes from the fact that in SUN gauge theories at large N on covered spaces, they exhibit, so they have a confined phase and a deconfined phase. So they exhibit a confinement and deconfinement phase transition, which also has a bulk tool. Actually, it's called the Hawking-Page phase transition. So in the deconfined phase, the energy is proportional to some number. So order n to the 0. Whereas in the deconfined phase, all the thermodynamic quantities are proportional to n squared, or to c, the central charge. And so there is a scaling relation between the thermodynamic quantities. So if you rescale S and the conserved quantities like angular momentum or electric charge, and you rescale n squared or c, then the energy also scales with alpha. And from this scaling relation, you can very easily derive this large N ordinary equation by taking derivative with respect to alpha and setting alpha equal to 1. So usually, the standard ordinary equation is derived from the scaling relation where you also have an alpha sitting here. And then you get an extra PV term. But now we don't have a PV term. And notice that this mu c appears here, where mu is the chemical potential associated to c. So in more detail, so in this previous formula, I had the energy, entropy, conserved quantities, and central charge, but there are also conjugate quantities, which are defined through the boundary first law in this way. So the temperature is the conjugate quantity of entropy, this is the pressure, and then there are chemical potentials associated to the conserved quantities B, and then there is the chemical potential mu associated to C, or n squared. And so what's very interesting is that we actually need this chemical potential mu in order to write down a consistent order equation. Consistent order equation. All right. So next, this is also a bit technical, but bear with me. So here I also stated that the bulk first law is dual to this boundary first law. And proven this in paper, you don't have to know all the details, but the way it works is that you kind of rewrite this first law in a certain way, that it takes this form. So I actually use the fact that lambda is proportional to 1 over L squared, and I used the smart equation, so I plugged in what is theta in terms of the other quantities in here, and then I rewrote it a bit, and you get this equation. And what's important is that if you use the holographic dictionary, this is precisely equal to this boundary first law. So the holographic dictionary relates, so R is related to the boundary curvature radius, that's like this radius of the sphere, the boundary sphere. Then the energy is related to the mass times this factor, so L is the ADS radius, there's this ratio of the bulk curvature radius and the boundary curvature radius. T is the temperature, omega is the angular velocity, and phi is the electric potential. So if you use this dictionary, you plug it in here, then you get this equation, right? But now, actually, there are two equations for the pressure and the chemical potential that follow from the bulk. So the pressure, you can see it from here, has to be proportional to n, right? Divided by d minus 1. So if you rewrite that in CFT quantities, you get the CFT equation of states. So that just follows from this rewriting of the bulk first law. And similarly for the chemical potential mu, you get this equation. But this is precisely the order equation that I have shown you before. So from relating the bulk first law to the boundary first law, you get these equations for free. Okay, so to sum up, what are the resolutions of the puzzles for black hole thermodynamics? So why does puzzle 1, why does black hole entropy scale with the horizon area? Well, in holography, black hole entropy is dual to the thermal entropy of a large engaged theory in the deconfined phase. And this thermal entropy scales with n squared, or the central charge, which is proportional to the horizon area. Secondly, the second puzzle is where are the work terms, or PVV and mu/dn terms in the first law of black hole mechanics? Well, they are actually present in the extended boundary, CFT first law. And the third puzzle was, can the smart formula be written without the dimension-dependent factors? The answer is yes, but you don't get the standard order equation, which holds for extensive systems, but you get a large N order equation. Okay, so to conclude, holography resolves some old puzzles of black hole thermodynamics. It's a heuristic principle with many interpretations, and I distinguish two forms, but it's probably very useful in research for quantum gravity, just like Mach's principle and the equivalence principle helped in the development of general relativity. Yeah, I think that it's an important guiding principle to find the correct theory of quantum gravity. I'll stop there. Thank you.